Okay, so for this problem, if you're needing some help with it, I'm going to go over part A in this video. So the first question it's asking about this population growth data is, what is the growth factor? So remember, the growth factor is the repeated multiplier, an exponential function. Instead of having a repeated number that's added or subtracted, every time x goes up by 1, which would be linear change, and exponential change, you're looking for the repeated multiplier. What is the previous y value being multiplied by to get the next y value every time the x value goes up by 1? So in this one, years is x, population is y. And just like with linear change, if we were trying to find the rate of change, we would look for the change in y and divide it by the change in x. So we'd be using like subtraction. So you would do 180 minus 100, but this isn't linear change. We're looking for a multiplier. So your question is, what is 100 being multiplied by in order to get 180? And so since we're looking for a multiplier, in like what 100 times what is equal to 180. To find what this unknown is, we could divide both sides by 100. In other words, you're just to find this multiplier, you're just taking a y value and dividing it by the previous y value. And so in this case, when we divide 180 by 100, we get 1.8. So that means at each step, we're multiplying by 1.8. And so now I'm showing that each one of these you're multiplying by 1.8. If you actually take this data, and this is like scientific experimental field data collected from actual rabbit population, I mean, it's not quite perfect, so we're kind of doing a best fit line. So if you do 325 divided by 180, and then if we do 583 and divide it by 325, you'll see you do get about 1.8 each time. So if we do 320, I think it was 325 divided by 180, get about 1.8, and that's the same for the rest of them as well, is you get about 1.8. And so that's what we call the growth factor, is dividing a y value by the previous y value to see what each one is multiplied by to get the next. And we get, and they call this the b value, b equals 1.8. So to write an equation, remember in exponential form, an equation takes this form, a times b to the power of x. And so a is always your starting value, that's actually your y-intercept. And b is our growth factor. Or it would be a decay factor if that number was less than 1 and our values were getting smaller each time. So if we want to write an equation for this, we could say that the population, that's our y value for this one, would be population, is going to be equal to 100 because it starts at 100. And then every time, every year, that population is multiplied by 1.8 to get the new population for the year. So you're doing 100 times 1.8, and then that number times 1.8, and then that new number times 1.8 to get the new population each time. And so these are easy to use to solve for any y value by substituting in and x. So for each of these, you're just going to do e equals 100 times 1.8 to the power of 10. P equals 100 times 1.8 to the power of 25. And this is the one I'm going to focus on because you get some crazy numbers. Is P equals 100 times 1.8 to the 50th power. So for any of these, you're just using your calculator. I found it works best to use the scientific calculator. So you can go up here to the top left, you can change it to scientific, any of these other ones, but scientific has a little bit more robust tools for working with these big numbers. And so we're just taking 100 times 1.8. And then you're using this button over here, this x to the power of y, to get an exponent of your choice that's not a squared or a cubed. So I'm going to put in 50. And you get this humongous number. Now, don't worry about writing out every single digit. So on this one, we could just write 580, and then we have, looks like 4 sets of 3 digits. So going back over here, 580, and I'm just gonna, it's okay just to kind of fudge that number just a little bit. You don't have to have every single number. And if the number is this big, you obviously do not need any of the decimals either. It's okay just to round this to about 580. Now, if you're using a different calculator, you might have gotten something different in scientific notation. And I'm not sure if you guys have learned about scientific notation in previous grade levels. You might have done it last year with Mr. Chung or Tremaine, but you might have gotten something like 5.8, depending on your calculator, and it might have been times 10 to the power of 14, or depending on your calculator, you might have gotten 5.8, and then instead it has an E. It's just an easier way for your calculator to denote that this is a gigantic number, E14. And that E is your calculator's way of saying that there's an exponent, a base 10 exponent. It just means that this is times 10 to the 14th. And so if you've learned about scientific notation at times 10 to the 14th, that's telling you where your decimal is. So in my huge number up here, this 580, would that even be trillions? The decimal is way down here on the right. When it writes it as 5.8 times 10 to the 14th, it's just saying that that decimal place is actually not here at 5.8. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Your decimal is actually 14 places down the line to give you that value. Okay, so it's just scientific notation. It's a condensed way of writing really big or really small numbers by indicating where the decimal is using this power of 10. Because every time you multiply or divide something by 10, it just moves the decimal place left or right one spot. Okay, so a little sidebar on scientific notation. So the last part, number 4, after how many years will the rabbit population exceed 1 million? This one, I said this in one of the previous videos, so we're trying to figure out when 100 times 1.8 to the power of x or n or y or whatever you're using for your independent variable. It could be some other number because it's years. We're trying to figure out when that thing would be, should say equal then, when that's going to be greater than 1 million. Now with our math right now, we don't have a way to solve backwards for x. You can't just divide by 100 and then like take the 1.8 root of the number. It actually involves non-base 10 logarithms. Go ahead and dig it out if you want to. It's probably in Algebra 2 in Khan Academy if you want to learn about this. But right now we can actually just use a little bit of just kind of hunting and pecking using a calculator. So on this one, if we go back to that calculator, you're just going to do 100 times 1.8, and then you're going to do times 1.8, and I think if you just keep hitting the equals sign, notice over on the left sidebar, you start getting, every time it just repeatedly multiplies by 1.8 every time I hit the equal sign now. So what you can really do when you're looking for it to cross 1 million is just count how many times you multiplied by 1.8. There's once, twice, 3 times, 4 times, 5 times, 6 times, then 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and there we passed 1 million. So somewhere between 15 and 16 years